So last time we talked about sort of more general blockchain and Bitcoin. Bitcoin is more of a sort of very specific. It's for cryptocurrency. It's for managing this notion of money. Whereas Ethereum is a lot more general, as we'll see. So for people who missed last time's session, we have this quick disclaimer where this series is meant to be like a general exploration, get you started on things. We don't go deep enough. So if you're interested in this kind of stuff, feel free to reach out and also ask questions during the workshop. If anything's not clear, sometimes I go a bit too fast, assuming people know about things, but people clearly don't know about things. So please interrupt us. Yeah, so last time we started with this example of wanting to create a ledger between friends. So imagine a scenario of going out to eat dinner with your friends, and then one person pays for, maybe the restaurant only takes one credit card, and you don't want to settle it right after on Venmo or on cash. So what do? You record how much everyone owes, and then perhaps you go out to dinner together multiple times. So every time a different person pays, and you just have a history of this time this person owes how much, this person paid how much. And then by looking at this history, you're able to just add up the numbers, the credits and debits, and this ledger, which is sort of a record book of monetary transactions, essentially turns into a notion of value, and you can use this ledger to track value, which is what money is. And important attributes of this ledger is these three big words. Non-invertibility means that once you guys all agree that person A owes $30, person A cannot go back and change that number, because if they can, then it messes things up. They can arbitrarily give themselves more money. The second one, non-repudiation, it means that you can pretend to be other people, and other people cannot pretend to be you. So once other people cannot just say, you owe me however much money without you agreeing to it. And lastly is the notion of consensus. Essentially, everyone in the group needs to agree that this is how much everyone owes. It can't be like, you believe you owe your friends $20, and your friends believe you owe him or her, $100. So that becomes a problem once you want to settle. And we introduced blockchain as a solution. So we'll go over some examples right after, but there's a notion of hashing. And when you chain the hashes together, you have hash chaining. And you hear the word chaining, and that's the same chaining as the blockchain's chain. And then you have public-private key cryptography to ensure you are who you are. And proof of work to ensure everyone agrees on sort of one piece of ground truth, however much money everyone has and owes. We wrapped up the class with a classroom blockchain activity where people pretended to be blockchain. And we'll do something similar today, in fact. So there's a quick animation. Let's see if I can control this. Perfect. You see this? Okay, cool, yeah. So we have a logbook, just like this, right? And if we were to record monetary transactions in this becomes a ledger. And this definition of ledger goes way back, so it's not a new thing at all. You would add transactions, A send B $20 or 20 Bitcoins. You add another transaction, you add another transaction. And you add these transactions based on time, and newer transaction gets added to later. So you maintain this history. And to use the blockchain, blockchain is a ledger. So you first need to create these accounts. So this is what we refer to as public-private key pair, public-private cryptography, to make sure that only you have access to your account and only you can authorize, transferring money to other people. Just like, only you can take your wallet out and give the money to someone else. So we're simulating this notion in the digital format. And then for Bitcoin specifically, because it's meant for monetary transfer, so users can request to perform actions and specifically transfers. PKA, this user can send a request to send PKB 10 Bitcoin, and then they need to sign it so that they set this rather than their friend B trying to take money out of their friend's pocket. Similarly, for C, wants to send 20 Bitcoin to PKA. Then we have essentially this notion of UPS delivery truck, so a network, a relayer that collects all these requests and then send them to blockchain. Blockchain, in fact, consists of not just one computer, but consists of a group of computers running blockchain software, and then every one of them sort of have a copy of this ledger. So one person first accepts, okay, cool, we have these new incoming transactions. And then everyone needs to sign off on it, agree on it. Then everyone updates their ledger. So we achieve consensus. Everyone agreed to the same sort of history of who sent however much money, who have however much money once you aggregate the amount together. And so for each time window where transactions are sent, we call that a block. And then similarly, so at time period 2, window number 2, so we have PKA and B trying to send requests. They get picked up, sent to the blockchain. Everyone agrees on it. Great. They're added to the blockchain, the ledger, as block 2. Now, this is probably not the usual format that you would see blockchain transactions as. This is what you would usually see blockchain transactions. So essentially, we abstract out this notion of a logbook, but rather just look at these transactions in series in the blocks that they are aggregated into. So block 1 came before block 2, and obviously all these transactions attached with the signature of whoever sent this transaction. Now we talked about hash function. So essentially, you're able to pass data of this entire block, all these transactions, into the SHA-256. It's a specific hash function, and it spits out a hash, which is a number, a string of seemingly random-looking, characters and numbers, and it's a very efficient way to sort of get a seal on these transactions, because for hash, once you change something in the original data, so if you change something in block 1, then the hash would come out to be different. So now we moved on to the notion of hash chaining. So you put the hash of one block into the next block, and then so that hash from the previous block becomes part of the block 2. Why is this important? Because if someone tries to change the history of blockchain, let's say Bob tries to change the first transaction from 10 Bitcoin to 100 Bitcoin, then the hash from block 1 changes color, it changes into something different. And because now the hash of block 1 is stored in block 2, it in turn changes color and it propagates all the way to the end. And then you have the last hash also change color. So it's super easy to catch cheating or people trying to modify the history of blockchain by only monitoring that very last hash. So this is a really quick summary of our class last time. So what happens after Bitcoin? Bitcoin was a success. It sort of created the category of cryptocurrency, and it's also sort of, it made blockchain useful, because before blockchain is just this theoretical notion that these enthusiasts talk about, but now it's like it's real and there's an application. So to think about Bitcoin, it's like cars with internal combustion engine, right? So cars made internal combustion engine like a lot more meaningful than before. Obviously, they're used in machineries elsewhere, but that's sort of the analogy. And the success inspired a lot other cryptocurrencies, as well as just general using blockchain to do useful things attempts. So some examples include Litecoin, which is a lighter and faster Bitcoin. We talked about Bitcoin's block confirmation is 40 minutes. So if you try to spend money 40 minutes later, then you actually spend that money, and the vendors agrees that you send them the money. That also obviously doesn't work, so Litecoin is designed to be much faster, so you can actually use it in your daily transactions. Zcash fixes Bitcoin's problem of being public. Zcash makes sure that whoever you send money to is anonymous, so everyone can remain anonymous on the Bitcoin, on Zcash, on the blockchain. Yeah. So what's missing? One thing is reusable infrastructure. What is reusable infrastructure? Think about launching an e-commerce site. You want to sell some products to the internet. That's a terrible way to say it, but to the people on the internet. What would you do? back in the days, back in maybe 2002, you have to set up your own e-commerce website. You need to buy your own server, like literally buy the servers, and put it in your garage. You just write the code to set up the website. You need to hire the marketing team. You need to set up everything. Whereas today, you can just worry about the product and put them on Amazon, and that's sort of everything down below is shared. So you have the shared infrastructure, and it's much more. It's much easier for whoever wants to launch, who only cares about launching products. So similarly for blockchain, right? Like if you just want to make a faster Bitcoin, why do you have to redesign everything below, right? You just use the same infrastructure and change your logic at the very top layer. The other thing is sort of more advanced programmability. There is a notion of scripts in Bitcoin, so it allows Bitcoin to be a bit more programmable, but it's very limited. It only allows so rather than Bitcoin, it's like one person agreed to, like, I'm A, I want to send B money. A have to sign off on this transaction, right? Bitcoin's programmability allows you to introduce maybe like not only A and B needs to sign off on this transaction to send the money to someone else. So it has very weak programmability, but what if you want to do something more fancy, right? What if you don't want to send money? You just want to do some computations. So Bitcoin certainly don't accept that, and that is why later Ethereum came into play. So Ethereum is another blockchain, and it's so much more than cryptocurrencies. It was conceived in 2013, and it was launched in 2015. It introduces the concept of smart contracts. Smart contract itself goes way back, perhaps 20, 30 years ago, but it's really the first blockchain that made it work. These are programs that lives on blockchain. So an example of these programs or app, I'm going to use these words interchangeably, is you can have an app that is cryptocurrency. You can have an app that is a membership organization and you sort of make decisions by voting. You can make an app where it's a game that players purchase, collect, breed, and sell virtual cats, right? An example, sort of analogy is like, it's like a smartphone. So when you buy your smartphone, it comes with the default functionality. You can make a call, you can send text, you can take notes, right? These are like, I'm an Apple person, so these are what iOS comes with. But you can go to App Store and you can install a lot more apps, and you can have a lot more functionalities, right? You can have Snapchat, you can have, back in the day there was a flashlight app, now it's part of the system. There's a lot of possibilities. But unlike a smartphone, it's not this one device that you hold in your hand, but rather it's like hundreds, thousands of smartphones that all have replicated state. They're all copies of each other that lives on, sort of the software lives on different people's computer. So that sort of, the benefit is that, if one of your phone dies, not that everything just dies, right? It has all these copies that, is kept safely. And going back to the hash chaining concept, once we detect one copy is broken or someone tried to change it, we simply discard it, and then we look at the other versions that is correct. So far, any questions? Yes?
What do you mean by distributed state? I could not understand.
So you have your computer, if there's a virus, right? Your computer is gone, right? Software is gone. But if you rather have like two backups, right? Maybe they're backup hard drives, or maybe they're actual computers. You're like that rich, so you can just have like two backup computers. And once one computer, gets infected by a virus, you simply move on to the other computers, right? So rather than having one state, you have multiple states. And for something like a blockchain, right? They usually have thousands, tens of thousands, hundreds of thousands of these replicas. So they're very robust. Anything else? Cool. This is a graph illustrating it. Yes?
So are all the replicas holding the same information, or does it differ from copy to copy?
Generally, they hold the same information, and that is sort of why we talked about consensus. So whenever you change something on one computer, let's say you type additional A on one computer, then every other computer needs to agree, okay, cool, we received the input of the A. Let's all update it. Let's all add an A. So there is sort of a moment in time where they're different when that first A is inputted on one computer, but very quickly everyone agrees on that. Oh yeah, so 20 years ago you need to carry all these, but now they all live on one smartphone. So they have this shared infrastructure of the smartphone, and they can instead just be apps on top of this smartphone. How does it work? So as we discussed, it's a giant distributed computer, so it has many copies of the same set of data. And users, just like Bitcoin, can create accounts in a very much similar fashion, right? It uses public-private key cryptography. And these accounts are used first for authentication. So it proves you are you. So when you say something, do something on the blockchain, it can always be traced back to you did that. And for a second purpose is that it can provide payment. So Ethereum, just like Bitcoin, it uses Bitcoin as payment. Ethereum uses ETH as payment. So you're able to sort of send some kind of digital money to other people. And this can be very useful as we will discuss. Users can ask computers to do things such as install programs, install apps. This could be apps written by other people or written by themselves. They can run apps, run programs, and this could be installed by other people or installed by themselves. So if other people install this program, then whoever installed the program must give you the permission to use their program. However, by default, any app can be used by anybody. And lastly, you have sort of many ways to read and write data with this computer. Requests are just like Bitcoin are submitted to this EVM computer in blocks. Does anyone know why? I think we briefly mentioned last time. So what if it's not submitted in blocks? What if it's one transaction is one block rather than a bundle of transactions is in one block? What would be a problem? Think about consensus. If I type an essay, go ahead. You have
I'm not sure, but if
Yes.
there's some, if it's like a whole big text and like you have to make some change, whereas if they're divided into blocks and you have to sort of change some part of that, it's much easier in comparison to when you have like a full block. Is that something?
I think you might be. I think you're on the right track, right? So if you have an essay, right? Everyone has this essay on their computer right now, and I want to make a change. And every time I make a change, I need to make sure everyone also, make the proper change. If I want to sort of do it one character at a time, I type one character and I need to talk to everyone. Hey, add this character, right? And then I type the next character. Hey, everyone, change this character, right? Versus, I'll write one sentence and then say, everyone, add this sentence. Because it takes so much effort to get consensus, to get everyone else to do the same thing as you. That's why we put things in batches rather than doing things at the sort of finest granularity. It just takes too much work.
I think we have another.
Oh, yes.
Would it also, would that be an example of, an intentional branching? Say it was only one blockchain, and then suddenly you just create 2 or 3 or 4 or 5 blocks, people don't know which one to add to?
Yeah, so you could argue that it reduces chance of creating these branches because you have, less of these decisions to make, right? So consensus, ideally, every time everyone agrees and don't create branches, but it's very expensive. So you want to sort of minimize the times you try to get these consensus. Yeah. Good? All right. Yeah, moving on. So these computers execute requests, incoming requests in some order. For the Bitcoin example, these requests are send money. That's the only thing, right? But for EVM, because now it's a computer, right? You can say, I want to click, or I want to load a program. You have a lot more possibilities. However, because we inherited the terminology from Bitcoin, these requests are still called transactions. And lastly, what's important about EVM is that the code being run on the EVM. So anytime you ask, the EVM to run a piece of software, everything the computer is doing in the background is very transparent. This is a very unfamiliar notion to all of you because almost all of the computer system or smartphone that you interact with, you do something, you don't know what the computer is doing, right? You don't know what the CPU is actually, what instructions it's processing. However, on blockchain, it's all transparent. So you know exactly what you're getting into. before you make that click. And after that click, you can see exactly the computer running code line by line and execute what you want. And lastly, the computer never stops, because if you have tens of thousands of computers, and as long as one of them is running, this computer keeps running. It's not like our computer, we just close the lid and it stops running, basically. So that's the benefit. Ethereum makes blockchain useful beyond cryptocurrency. So first of all, you can create more cryptocurrencies. They're called tokens in Ethereum. So you can generate new tokens very easily. It takes like 5 seconds if you know what you're doing. You can do DeFi, decentralized finance. We could dive into this later. It's basically a piece of software. You have DAOs, decentralized autonomous organizations, NFTs, gaming, metaverse, a lot of possibilities. We still don't know what we're able to do with blockchain at this today. We know some of them work, some of them failed. Yeah. I want to explain a bit more and how this distributed computer work by introducing a blockchain TI-84 calculator, because I consider a calculator to be the simplest form of computers. So here we have a TI-84 plus calculator. Last time I saw a real one of these is probably in middle school. You can compute using operators like add, subtract, multiply, and divide. And you can consider these operators as the most simple program, right? You feed in two numbers, it spits out another number, right? These are sort of synonymous to programs. And you can store, it has storage, so you can store variables and use them in future operations. I was first introduced this to probably also in middle school, so you can, what's the button that you actually press? It's like second and something, and you can store the output into these slots into the calculator, and you can use them later. And for our purpose, let's assume we have A, B, C, D, 4 slots, and everything is set to 1 initially. We also can read variables and use them in computation. So once you store something, or you didn't, let's say you start with 1 and A, B, C, D, then you try to read B, A, B, C, D, they're all going to give you 1. And in this case, well, that's a terrible example. Yeah. But if you assume everything is set to 1, right? You take A plus B, you're going to get 2. And so here we're going to introduce sort of blockchain plus calculator, but only one transaction per block. At the beginning, like we said, A, B, C, D are all set to 1. And we have our first transaction in this block. This program is B equals A plus C. So what's going to happen to A, B, C, D? Hands. So you're going to start with 1, 1, 1, 1. And you run B equals A plus C, what's going to happen to the state? Yes?
B changes to 2.
Precisely. And nothing else changes. Great, so B is now changed to 2. Now we handle the next request, right? So at time 2, we receive this one request to run program 2. And it's a little complicated, right? So first we set D to be 5, and then we set A to be the sum of D plus C. Volunteers? To do this quick math? Yes?
So A is 6.
A is 6? Yes, that's right. So A is 6, B is still 2, C is 1, D is 5. So this is how the computer operates, except you have a lot of these requests coming in. So we have these TI-84 calculators by processing one request, it moves to the next moment in time, the next moment in time, next moment in time, and it just moves forward. Obviously, each moment in time, it would process more than just one program. It would process many, many programs. And from this, you can easily interpolate this to a more complex computer, right? At moment A, you click on Chrome browser. At moment 2, you open a new tab. Obviously, for our user interface computers, it's really hard to accept multiple people's requests at the same time, because one person could be like open browser, the other people like close browser, open close, right? But if you're doing sort of more lower level computations, or you're using different apps, it makes it easy and it does work. Is this free? is Ethereum free? It sounds like, why are we still using computers anymore, right? Like, why don't we just use Ethereum instead? First of all, it doesn't support, opening Word or, do Excel computations. No, it doesn't. So it's sort of computers designed for some specific use cases. And second, you do have to pay for this computer. As we said, Ethereum supports accounts, and you have these ETH you can use to pay for stuff, and ETH is precisely the currency you use to pay for this computer, the EVM. EVM stands for Ethereum Virtual Machine. And why is it a virtual machine? Because it's not really one machine that runs on one computer, but it's sort of this concept of machine that actually consists of a lot of computers. So more complex requests is going to be more expensive. For example, a simple transfer, just like Bitcoin, is cheap. It takes 21K gas. Gas is this way of sort of tallying up how complex things are. So transfer is 21K. Minting an NFT is a more complex process. So it's going to take 75K plus, up to 100 something K. I was looking through some transaction, and these are the number I got. Also, the gas is not just one price. You can think of it as when you go to the gas station, based on how, let's say, 100 miles of driving takes 1 gallon of gas, right? So 100 miles is always going to take 1 gallon of gas for your car. But the price of gas fluctuates based on a market of supply and demand. So transfer is always going to cost you 21K gas. That's like 21 gallons of gas, right? But the price can fluctuate. So actually how much it costs in US dollar terms to transfer actually fluctuates over time. So, and these fees are paid to the computer that runs the blockchain. So we mentioned earlier that blockchain runs on these replicas of machines, and they all achieve consensus whenever a request is processed. So the machines don't run for free. They pay for electricity and pay for hardware. So the fees are actually distributed to these sort of physical embodiments of Ethereum blockchain. Although the rule is kind of weird. Some of the fees actually disappear into thin air. They just disappear. So they don't get paid 100%. Any questions so far? Next time I need to do a Quizlet or Kahoot so I can ask questions, because I don't know if you guys really don't have questions or you're just afraid to ask. So here we're gonna, yes? Do we have a hand? No? No. Okay. Here we have a case study. Why do we talk about Ethereum, and what kind of programs can we run on it that would be useful? One example is an auction. What is an auction? The goal of an auction is that people can submit bids for a certain item. They must have enough money for a bid. I can't just say, raise 300 million, right? I don't have 300 million. So that's going to mess up the auction. We don't want that. And then the person who wins the prize pays the price, right? So if I win the bid for 300 million, I need to pay, right? I can't just be like, I pull out, or I don't have any money to pay for the item. And so whoever who participated in the process, right? Like I lost, I didn't get the winning bid. My money wouldn't be, taken by the auction house. So these are some of the goals. How can an auction go wrong in reality? Bidders can submit fake bids, right? They can submit it on behalf of other people, right? Like I can submit a bid on behalf of Warren Buffett, right? He has a lot of money, but he's not, giving me the right to manage his money, or I don't have enough money and I, submit a 300 million bid. And auction house can also carry a lot of risk. They can rig the auction. They can sell at a lower price than possible, right? Like, for example, they just decided, they want to buy the item, and then they keep the high-paying people out, and then they just end up getting the item for cheap. Or once someone wins a bid, they don't actually give the item to them. That's also a source of a mode of failure. Lastly, you have winners. We already mentioned this, right? Winners don't want to pay for the winning bid, right? Then we need to run the auction again. It's costly for everyone, right? Cool. Brendan?
Yeah, so now we're going to simulate the interaction of how, like, I guess smart contracts really work in the Ethereum network. Here in my hands, I have some network cards, and one of it is the smart contract deployment. On each card, you will find some code that represents like the function that each smart contract has. And this notion of me passing down, I guess, these network cards is like a notion of the sender of the smart contract deploying the smart contract.
So every one of you is an Ethereum node or one of the computers that runs the software. So at moment zero, you don't know anything. Nothing is on your hands. You don't have any smart contract installed. You don't have internal states. And Brendan is sending you these cards to install the smart contract, the smart auction. No, the auction smart contracts into your hands. So now you have a piece of code in your hands. And it will tell you to update whatever you have stored in your states accordingly.
And on Ethereum, there are many of smart contracts just like this. It has the code as well as the current state. How about a close read of the code and the, I guess, like the data fields on the data side, and we can proceed.
And do they need a pen or something?
If you guys have a pen, that would be great because you do need to write down some data as we pass along.
Yes. Right. You're a computer. You have a program. You have data fields that you can update. That's what you are, right? Okay.
So as you can see, this links back to the idea that we just talked about, right? Every single one of you have the same copy of the code and data fields. Although you guys are different computers, but this information is replicated on every single node in the entire network. So if any one of you maybe became sick, like today as of right now, and went offline, everyone else still has the same data, and the data is still there to be executable.
Okay, cool. So we're gonna move on to the first action now.
Yeah.
Okay, so at time that was time zero, right? So at time one, Alice bids $100. Right. So now Alice decides to tell everyone in the network that she bid $100.
And by telling everyone, what she literally does is send a network request, and which is represented in this call. Again, take a look at what's written on the card and see if it invokes anything that's written on the previous smart contract calls.
So you should all see that you have Alice bid $100, and you see Alice's signature on it. So do you see the signature on it? Okay, cool. So you know it's legit, right? Alice did actually bid $100. And what should they do?
And, well, before we call to the end of this round, right, remember, we're bundling transaction in a single round. And other people can be sending transactions at the same time. And here we have Bob, who wants to mimic as Alice, right? But Bob doesn't have Alice's signature. Bob's trying to send another transaction, try to like, I guess, mimic as Alice, but Bob can only use his own signature. So look at what's the definition of the function calls on your smart contract deployment card and see whether or not that would do anything to the current state of the smart contract. As in, does Bob's signature matches the bidder's name on the smart contract call? And please write down what you think the current state of the smart contract will be after the end of round one.
Once you're done, please look up. Wow, this is so classic. So I know, you're done. I'm like a professor. Wow, that's crazy. All All right, I'm gonna assume that you're generally done, or I'll explain how it works.
Yep.
So, as we said, right, the second car that Bob pretended to be Alice, we're going to reject that, consider that invalid. But the first one, Alice bid $100, we're going to consider that valid and change our state, who the top bidder is and who the top bid is. So now we have the state of the machine that everyone agrees on is top bid 100 and top bidder is Alice. Cool. And then, do you have this? Or
Yeah,
no?
and then we move on to round 2, right? Same idea again, but this time I'm not going to pass it to you one by one. I'm going to let you broadcast node by node. So I'm going to start with one node. You're going to pass it down to your IO. And eventually, without me having to individually talk to each of the nodes, this transaction is broadcasted. This is what the gossip protocol within Ethereum is. Each of the nodes can talk to each other. Oh, we might not have enough, so. One of you might need to
We have part of the network dead. That's terrible.
Would you participate and
Right. So if you're a sys major and you're taking 553 right now, you would know that the internet is rigged for not efficiency, but just to make things work. So it's very possible that we send things to one end of the network, and then that person has to run all the way to the other end and deliver that message. It's not very efficient, but it works. Yes.
Does the top bid carry over between rounds?
The what?
The top bid?
The top bid does carry. It carries all over. Right?
Yeah. That's why you have a fixed state that can be updated after each.
That's why you have a single piece of paper that records your state. Yeah.
Question?
For start time and end time, is that cumulative? So the end time of round 1 is the start time of round 2, or no?
So looking back at the slides, right, we didn't specify that the end round should be set as round 4. That's just basically how 10 minutes is counted. So in this example, the starting round will be round 1, and the end round will be round 4.
Yeah.
That's why we also only reserve 4 spaces for you to write things down.
Yeah, we sort of didn't make that very valid simulation, so you can ignore that.
Yeah, just remember, a lot of these things are abstracted. There is so much more details in the fine grains of the network, but we just hope by using this interaction, you can have a better understanding of how smart contract calls and deployment really work.
Yes.
So with the first one where Bob sent stuff through Alice's name, did our function actually check the signature at all, or?
So the function on there, Brendan,
Yeah,
go
would
ahead.
you like to read this fine line very well? So you can see if, I guess in that case, if you put bidder's name down, and it checks whether or not the bidder equals to the signature.
Oh,
yeah.
my bad. Okay.
So essentially, we always we don't want to take inauthentic bits, right? So whenever you're doing things on blockchain, almost always you're checking for the authenticity of whoever's sending the stuff. Okay, cool. So Bob sent bid 90. Yes.
Sorry, where was the line?
Yeah, Bob bid $90, so that's a pass.
So,
But
yeah,
it's not a top bid, right? Because 90 is less than 100. So we don't update the state. So it's still 100.
This line is pretty much included.
Still nothing that explicitly checks.
All right, cool. And next round, we have Charlie bid $200.
This is round 3.
This is round 3.
Okay.
Pass this down again.
Wow, this is actually pretty fun. I wish I'm in your seat.
Does this still count as a round, even if it's invalid?
So in a given round, right, or in a given block, you can have a lot of transactions. You can have people who are valid that you accept. You can have invalid ones that you reject.
Does
So
anyone
round
have an
is
extra
because we're trying to simulate blocks. So a block is actually a window of time. So it's within 10 minutes you receive 10 requests. Maybe 5 of them are fake, but you register the fact that's real. Cool. So everyone got Charlie bid 200, and based on the algorithm, based on the smart contract, now you update the top bid to be 200. Top bidder Charlie. And at time 4, do we have a time 4?
Yes.
Oh, we have a time 4. Crazy. This is real.
again, remember this is time 4. You're also checking like the current round time. So what does that mean? It means your smart contract is ending. So this is the last round for anyone to bid anything.
What's Bob do? Oh, this is one of the times.
What's going on?
So at time 4, you decide that this was the designated end time, and you don't want the auction to go on forever. So this is how when the auction ends. The smart contract never ends, but the auction ends, right? And then from now on, Charlie, as a winner, because he is recorded as a top bidder, will claim the NFT, so he gets the NFT, and everyone else who's put the money to send the money along with the request. In this case, only Alice gets her $100 back, and now everyone's happy.
Yeah.
So
This is because if you read the fine lines on the code, there is this one line saying Alice's money will be put in an escrow, which means that her money will be held there temporarily, such that she cannot launch like a spam attack on the smart contract.
Right.
She cannot fake putting down like $1 million for putting this as a bid if she doesn't have the money.
Right. And so how does the real auction house work, right? Like maybe you don't actually transfer the money into auction house bank account, but they'll do their due diligence and background check to see that you have the ability to afford that. And also, why don't we do that in real life? That we take clients' money into custody for things like auction. That's because it's like it's expensive to transfer money, and you don't know auction house is going to be taking care of your money properly. But with a smart contract, because you know exactly what it does, it literally doesn't have a line of code that says take your money and run. So you're able to sort of just pass the money along because you will get it back unless you win the bid. So we have the previous slide, auction gone wrong, and now we essentially check at all the ways that the auction could fail in a normal setting and versus what we implement in a smart contract. So first of all, winner don't want to pay the bid. Impossible, right? Because their money is already taken, and once the bid ends, the auction ends, they're able to take their price. And then the other one, submit fake bids. Impossible. They can't submit on behalf of other people, just like Bob, and they can't not have enough money because they actually need to send the money to the escrow account, which in this case is a smart contract. And can the auction house rig the auction? No, impossible, because everything is transparent. It's right in front of you. That's all the smart contract can do, right? The auction house doesn't have sort of free will. So it only executes the code. And can it try to like sneak their way into selling to an affiliated party at a lower price? No, because everyone can send bids, and as long as you have the highest bid, you get the price. And not paying out, no. Again, it's a code. It says you as long as you win the bid, you're able to get your item. So how do we write a smart contract like this? What do we have on there? Oh, it's a pseudocode. Yeah. Perfect. So obviously you don't write it with pseudocode. How do you write a smart contract? You use the most popular language is this thing called Solidity. And how does Solidity, which is human readable code that it's like if, else, whatever, it then gets compiled into bytecode. So what is bytecode? That's hard to explain. So it gets translated to a format that machine reads more easily. And that bytecode gets uploaded to the blockchain into every one of your computer that runs Ethereum. And then whenever called, it would execute that bytecode. And Solidity is a high-level programming language for implementing smart contract. And if you know anything about coding, familiar with JavaScript with TypeScript, okay, JavaScript, TypeScript, like Python, it's somewhat similar to that, even a little bit similar to Java, because these are programming languages. So it's object-oriented, not too important if you're not into CS. But that's not the only smart contract programming language. Right, for Bitcoin, we mentioned Bitcoin scripting language, which is sort of very weak notion of programmability. Ethereum, you have a few different options. Other blockchains, they have their own blockchain programming languages. If you want to learn more about Solidity and learn how to deploy your own contract and run your own contract, come next Wednesday. We'll teach you how to. Yes. And as we previously talked about Ethereum applications such as NFT. What are NFTs, right? Like you know NFTs as these, digital collectible JPEGs, right? But what are they? They really are just a sort of a standard of code. So it's like as long as your code has these three data fields, these variables, and it supports, transferring, minting, and maybe one more thing, right? That is an NFT. So it's just sort of almost a format of code. Think of it as Wharton 101 teaches us like how do you give a presentation. First step, you have an outline, introduce the team, and then a few steps, and then you have a conclusion, right? Anything that fits that format is NFT, and that format is called ERC 721. So NFT is just a format, right? What do you put in it, and what you want to do is your choice. So I want to make the argument that the technology and the applications are very separate, and NFT could be much more than just JPEGs. DeFi, decentralized finance. So just like how we created the auction with smart contract, you can create lending. You can create staking, which is similar to sort of deposit, and you get interest. You can get what else? You can have insurance companies run fully on smart contract, right? It's the possibilities are endless. You have more infrastructure stuff like MetaMask or your wallet. Again, if you come next class, we'll get you set up. And you have Uniswap. It helps you. It's a market. It's a marketplace. It helps you convert one type of token to the other. It's like Forex, right? You convert US dollar to Japan JPY, Japan yen. Yeah. So Compound is sort of more DeFi lending stuff, and DAOs, voting governance. It's just like what we did with auction, right? Like imagine you have people vote on a certain topic, and then people continue voting, and you move your organization forward. Yeah. So the majority of the class we have already finished, but at the end we just want to address a few topics that you may have heard of, but not sure what's going on. So what is the merge? For Bitcoin, we talked about proof of work as a consensus. So everyone solves a cryptographic puzzle to make sure no one is cheating. However, the merge, essentially, Ethereum decided to switch to a different model of different model of consensus. It's called proof of stake, and it's more secure, and it also reduces Ethereum's energy consumption by 99.95. Because what is the problem with Bitcoin or a lot of cryptocurrency that you heard of is that they destroy the earth. They use like 3% of the global electricity, right? But after the merge, once we switch to proof of stake, Ethereum actually is now very incredibly green. It only does the necessary computations rather than trying to solve cryptographic puzzles, which is sort of meaningless, other than its purpose in consensus. Proof of stake, people argue that it's not proven because it's so new and it's not safe. However, it's really safe because how many computers that runs Ethereum software, right? There's 510,000 of these nodes. And to become one of these validators, you have to deposit 32 ETH, and the market price of ETH is around 1,500. So it's a decent amount of money. And if you make one mistake, your money is gone. So no one is incentivized to make mistakes. And so here are some specific algorithms of how people decide on sort of whose transactions should include and how to execute it and how to execute everything correctly. It's sort of like some kind of prisoner's dilemma where you're randomly chosen, and if you make a mistake, you would get your 32 ETH slash. Your money is taken, and it's really hard to cheat because if you want to cheat, you need to make sure everyone who gets randomly chosen from 510,000 validators, you only choose 128, and then you need to make sure that these 128 people agree with you. But because of how slim the chances are, it's really hard to pre-position these people because you don't know who gets chosen in each round. And if you want to have a good chance to cheat the network, you need to bribe like so many people, and also run a huge risk of getting all of your money taken away. Yeah, so it's really expensive and it's really unlikely for Ethereum network to go wrong. And then there's also a topic of scaling. So Ethereum, every second you can, so here the data is say 15, I don't know what the actual data right now is, but every second there's 15 transactions, 15 requests gets executed by Ethereum machine, right? That means if all of us submit a request to Ethereum, they cannot get executed in 1 second, right? Some go first, and someone go in the second batch. But there's a lot more people than just what we have in this classroom, right? Like so many people in the world try to use Ethereum. So it's not fast enough, right? There are a lot of factors that limits the speed of Ethereum. So essentially we want to scale up the capacity of the Ethereum network so we can do more. There's this notion of layer 1 versus layer 2. Layer 1 is something like a blockchain, so it's your vanilla blockchain. And layer 2, what you essentially do is like you compress, let's say 100 transactions into one transaction. Compress the data of 100 transactions into one transaction, and then put that transaction on Ethereum. So by doing so, you essentially multiply the bandwidth of a blockchain network by 100 times. And it's a problem of like how much you can compress the data back. There's a lot of details and a lot of things that you can learn about all of these topics that I just mentioned now. I encourage you to talk to us or do your own research after class. Yeah. So at the end we'll be sending out these links and the slide itself, and as well as the recording. So if you want to try your hands on implementing some of these smart contracts or learn more about Ethereum, you're free to do so. And you can always email me or email other people in Web3 builders for resources or help to get started on this kind of stuff. Yeah, and come to our next lesson next week, same time, and it's going to be intro to Solidity, which is create your first blockchain wallet, your first smart contract, and deploy your first smart contract. That's it. Okay, question? Yes.
Wait, so just like about the whole proof of stake thing, it's like